MAT-601, that is real analysis 2. So till today, so we have seen two chapters. So within a minute, I will just revise what we have seen in previous lectures. So yeah, so second chapter, just minute, yeah. So second chapter, it was continuous functions on metric spaces. So in that we have seen functions continuous on metric spaces. Then we have seen definition of open set, closed sets, some results on open sets, and then some results on closed sets. So that part we have seen in previous some lectures. So in this lecture, just a minute, we'll start next chapter. That is chapter number 3, compactness, completeness, and connectedness. So this is the main chapter of this course. So in this chapter we'll see, so first topic there is more about open sets, and then connected sets, then bounded sets and totally bounded sets, complete metric spaces, compact metric spaces, continuous functions on compact metric spaces, and uniform continuity. So total 7 points we'll see in the chapter. So let us continue. So first topic, there is more about open sets, that is 3.1. So let us introduce the following notations first, and then we will see some results on this. So let M be a metric space and A be any non-empty subset of M. Then what is open ball about A with radius R? So this is open ball in set A. So see, so what is BA? So BA denotes it is open ball in set A. What is capital A? Capital A is any subset of metric space M. So capital M is a metric space. Capital A, it is any subset of metric space M. Then what is open ball about A with radius R? So you can consider, yeah. Suppose it is M, that is metric space M, and I'm taking suppose set A. Suppose point A is here, point A is here, and if we draw open ball about A, so then just a minute, yeah. So you can see, so it will be open ball about A with radius R. So what is this? Open ball about A with radius R. R is any positive real number. Then what is the open ball about A with radius R in set A? So B to suffix A. So it contains only these points. So you can observe. So what is this? So it is only this part. It will contain only points of set A. So it contains all x belongs to A. It contains only elements or points of A. So whose distance from A is strictly less than R, means it contains all these points. So you can observe. See. So this is BA, sub capital B to suffix A. And what is BMAR? So it is open ball in M, and this is open ball in capital A. A is any subset of capital M. So it contains all x belongs to M such that, so rho of x is strictly less than R. So distance of all such points from A should be strictly less than R. So it contains whole open ball. So you can see what is open ball about A with radius R and suffix M. So it contains, you can see, it contains this whole open ball. See, so this total open ball in capital M will be this. It contains all x belongs to M, so that distance from A. So it contains all such x belongs to M such that distance from these points from A it should be strictly less than R. So then it is clear that, so you can observe. So what is open ball about A with radius R in A? So naturally it will be intersection of, see, open ball in M with A. So A intersection BMAR will be the open ball BAR. So naturally, so this relation is there. So this is useful relation which we'll use in future. So this relation, so this concept, it is different. So open ball in A and open ball in M. So these are two different things. So this open ball in M. So M is a metric space. Capital A is any subset of metric space M. Then what is open ball in A and what is open ball in M? So yeah. So there is one result. There's theorem. So let M rho be a metric space and let A be any proper subset of M. Then the subset G2 suffix A of A is an open subset of A rho. If and only if there exists an open subset GM of M rho such that, so we write GA as A intersection GM. So this is if and only if, means if GA is written in this form, that is if there exists a subset A of capital M such that we write GA as intersection of GM and A. So then naturally J will be open in A, and if J is open in A, then naturally it can be written in this form. So this statement of this theorem, and we'll skip proof of this theorem, so which is out of scope. So we'll continue next topic, that is 3.2, and it is connected sets. So again there is one theorem, and this theorem is nothing but, so this theorem indirectly gives us definition of connected sets. So let M rho be a metric space and let A be any subset of M. Then if A has either one of the following properties, it has the other. So if it satisfies A, then naturally it satisfies B, or if it satisfies B, then it satisfies A. So what is A? It is impossible to find non-empty subset A1 and A2 of M such that, so A can be written as union of A1 and A2, and A1 closure intersection A2 should be empty and A1 intersection A2 closure should be empty. So that is first condition. It means it is not possible to find such pair of sets A1 and A2 which satisfy these two conditions. So their union should be A and their intersection should be empty. So such two sets we cannot find. So that is A. And what is B? When A is itself regarded as a metric space, then there is no set except A and phi which is both open and closed in A rho. Means there are only A and phi are the closed and open subsets in A rho. So if A is true, then B is true. If B is true, then A is true. So this statement of this theorem. So I will repeat it again. See. So let M rho be a metric space and let A be any subset of M. Then if A has either one of the following properties, it has the other. So it is impossible to find non-empty subset A1 and A2 of M such that A, it is written as A1 union A2. So A1 closure intersection A2 should be empty, and A1 intersection A2 closure should be empty. So that is case condition A. And what is condition B? When A rho is itself regarded as metric space, then there is no set except A and phi which is both open and closed in A rho. So this theorem provides us partition of sets. So this pair A1 and A2 will be the partition for set A. So suppose if M is a metric space, see, and so M is a metric space, and suppose So A is any subset of M, then so this is A1 and this is A2. Let us see. So what is connected subset? So when you say is connected in M, it so if it satisfy A or it's satisfy B. If it satisfy A, then it satisfy naturally B, or if it satisfy B, then it will naturally satisfy A. So when we say is connected, so A1 union A2, it is not possible to find such pair that is A1 union A2 is equal to A and A1 intersection A2, or A1 closure intersection A2 should be empty, or A1 intersection A2 closure should be empty. So such pair does not exist there. So then naturally A will be connected set. So let us see. So what is the definition of connected set? So let M rho be a metric space and AB a subset of M if A has either and hence both of the properties A and B of previous theorem, we say that A is connected. Means, so this is connected set. See, so here A1 union A2 is A, but what is A1 closure? A1 closure will be this. So this line means this border will be common to both A1 and A2. So here, so A1 closure intersection A2 is not equal to empty. So in such a case, this set A will be connected set. Means for this set A, it is not possible to find such pair which satisfy condition A or condition B, and hence both. So if you take suppose A like this, means see, so this is suppose B set, both this and this. So in this case, I can write B as, suppose it is B1 and it is B2. So in this case, I will write B as B1 intersection B1 union B2. And what is B1 closure? So B1 closure will be again different from B2. So there is a clear cut gap between this B1 and B2. So naturally in this case, so what is B1 closure intersection B2? It will be empty, and again B1 intersection B2 closure, it will be empty. So in this case, so this pair B1 B2 provides partition for the set B, and hence B will be disconnected, or it is not connected set. So imply B is not connected set. It means it is disconnected set. But here you can observe A is connected set, because for A it is not possible to find such pair. So you can observe what is the definition of connected set and naturally definition of disconnected set. So this is definition of connected set. So next topic, that is 3.3, it is bounded sets and totally bounded. So first, what is the definition of bounded set? See, so what is the definition of bounded set? So let's suppose M rho be a metric space. So we say that the subset capital A of M is bounded if there exists a positive number L such that so rho of xy is less than or equal to L for all xy belongs to U. Means distance between any two points of A should be less than some fixed positive real number. So what is capital L? Capital L is fixed positive real number. So distance between any two points of set A should be either L or less than L. It means it should be finite. So distance between any two points of set A is finite, then naturally set A will be bounded set. Means, so if you take any two points from set A, so then that distance is always less than some fixed positive real number. So what is diameter of set? See, so next definition of diameter of set. So if A is bounded subset of metric space M, so we define the diameter of A. So what is the notation for diameter of A? So this will be notation diam A as So it is list upper bound of all row xy. What is x and y? So x and y varies in A. So it is list upper bound. It is the smallest upper bound of all distances. So naturally, it will be the largest distance between largest points or farthest points you can consider. So here both x and y are elements of A. So naturally, y is also element of A. So what is diameter of set A? Suppose if you take C. So this suppose M. So M means it is matrix space, and you can take suppose capital A is a subset of M. So what is the diameter of A? So diameter of A means it is the distance between farther or it is the longest distance between any two points. So if we take suppose one point here and another point here, so this distance, see, naturally this distance will be the diameter of A. So diameter of set, it is the least upper bound of all row xy where x and y varies in A. Means it is the longest distance between any two points of set A. So if A is not bounded, we define in that case diameter of A is infinity. So when we say diameter of set A is infinity, if it is not defined or if A is not bounded, means in that case we'll write its diameter as infinity. So this one note. So next definition, that is totally bounded set. So this is so next definition of totally bounded set. So let M rho be a metric space. The subset capital A of M is said to be totally bounded if given epsilon strictly greater than 0, there exists finite number of subsets. So for given epsilon strictly greater than 0, there should exist finite number of subsets. Suppose A1, A2 up to AN of M says that. So diameter of each A1, A2 up to AN should be strictly less than epsilon for K varies from 1 to n, and their union contains set A. So when we say, so A is totally bounded set. What is the definition of A is totally bounded set? See, so for every epsilon strictly greater than 0 or for given epsilon strictly greater than 0, always you should find finite number of subsets A1, A2 up to AN of M says that. So diameter of each set should be strictly less than epsilon and their union should contain A. Means A is contain union of these n sets. So in that case, we'll say A is totally bounded set. So yeah, there is one theorem. If the subset A of matrix space M rho is totally bounded, then A is bounded. Means, see, totally bounded implies bounded. But bounded does not imply totally bounded. Means totally bounded is broader concept than bounded. So every bounded set is not totally bounded, but every totally bounded set is bounded set. And yeah, a subset A of RD is totally bounded if it contains only finite number of points. So this is another note. Every bounded set in RD is totally bounded if it contains only finite number of points. So this is about totally bounded set. So we'll stop here, and in next lecture we'll continue, that is complete metric spaces. So